Okay, let's see now how we can apply linear regression to classification problem. So instead of having to predict the value of the output y, we would like to use that prediction to classify data points in black or white or 1 or 0. So of course we can use linear function for this classification task as well. So here's an example of how this would look like. So in that case, for example, you see data points in red and data points in green. Okay, so we would like to find the best line that splits the data into two distinct classes. So plot A here is seismic data parameters, body wave magnitude x1 and surface wave magnitude x2 for earthquakes. Okay, that's in earthquakes are in orange and nuclear explosions are in green. Okay, that's between 1982 and 1990 in Asia and the Middle East. And you can see the decision boundary here that tells us based on this measurement whether it's an earthquake or a nuclear explosion. You can see that with more data, okay, we can't really separate them using a line anymore, right? Because if you look at this line, above the line, we do have a nuclear explosion, and below the line here, you have a couple of earthquakes. So that means this data is no longer linearly separable. It can be separated by a simple straight line. So given this training data, then the task of classification is to learn a hypothesis H that, given a new measurement x1 and x2, returns whether 0 for earthquakes or 1 for explosion in that case. So this line right here, this is what we call the decision boundary line that separates the two classes. The linear decision boundary is called a linear separator, and the data on the left here is called linearly separate. And actually we can get the weights for the actual line here. As you can see, 0 intercept, we can get the weights for those. We can also think of H, whatever you're calculating here, as a threshold function, okay, which is a vector of weight w dot the input measurement x. Essentially, if H is above a certain threshold, it's an earthquake. If it's below the threshold, it's going to be considered a nuclear explosion. Okay, so H sometimes is called, in that case, the threshold function. So now that we have our mathematical definition for the hypothesis H, we're going to apply a similar procedure to what we just applied to minimize the loss function. But in this case, we have to change a little bit our definition of loss function, because we're not interested in how far the prediction is from the true value of y, but rather the number of correct classifications versus number of incorrect classifications. Okay, so for any given training point, if we predicted the correct class, then in that case the weight should be unchanged, right? Because we made a correct prediction. if we predicted a 1, if we predicted a 0 and the true classification is 1, then in that case we have to increase the weights a little bit to compensate for this error. When x is positive, we'll decrease it when x is negative, and vice versa. If we predicted a 1, like an earthquake, when it's actually a 0, a nuclear explosion, then in that case we have to reduce the weights a little bit for that given x if x is positive, and increase it when x is negative. Now this rule we just discussed is called the perceptron learning rule. Okay, so essentially it's going to adjust the weights based on the type of error and the sign of the input. Okay, so typically the learning rule we just discussed then is applied one example at a time by choosing random examples. Like we said earlier, we don't have to run the entire training data. We can just pick a mini batch and use the mini batch to evaluate the gradient, and then we can follow the metric here of how good we're doing as the training progresses. So here we're measuring the proportion correct, because that's what you're interested in. Of course, the goal is to reach 100% correct. So you can see that this is up to 700 steps. It's still no clear conversion. And then between 25,000 and 75,000 iterations. And then eventually, by the time we reach 75,000 iteration here, we're almost converged. Okay, we almost get 100% classification. So the training curve measures the classifier performance on a fixed training set as the learning process develops, one update at a time on the training set. We will see later how to use the training curve to pick a stopping point, because remember, we always run the risk of overfitting the data. We don't want to do that. So typically we don't wait until the model is able to predict every single training point, because that's probably going to lead to poor generalization. But you can see here that the conversion process isn't pretty, right? So it's not like we go in a smooth line up. It's possible that even here at 50,000, we still get some iterations where we're very far from the 100% classification accuracy. Now, that doesn't mean that the learning route does not converge. It does converge, but it's just not, monotonic convergence. Now, what happens if the data points are not linearly separated? We can't find a straight line boundary between the two classes. This situation is very common in the real world, obviously. Okay. So in that case, the perceptron learning rule will fail to converge even after 10,000 steps, as you can see from these graphs. Even though it did hit the minimum error many times, but the algorithm keeps changing the weights, okay, because it's impossible to find a line that will separate the data. So in general, the perceptron rule may not converge to stable solution for a fixed learning rate alpha. But if we decay the learning rate as a function of how many iterations we already ran, then the rule can be shown to converge to a minimum error solution. Okay, so that's why reducing the learning rate or decaying the learning rate as time processes is very important. So a modification of linear regression is what we call logistic regression. So we've seen that passing the output of a linear function through threshold function like we just did creates a linear classifier, but the hard nature of the threshold causes some problem, right? The hypothesis H is not differentiable, and actually it's discontinuous, so which makes getting the derivative very complicated and makes the learning process very unpredictable. You saw from the conversion there. Furthermore, the linear classifier always gives you 100% confident prediction of 1 or 0. So it doesn't give you really probability. We would like a classifier to say, well, there's a 75 probability or 76 probability that this is an earthquake and a 24% probability it's a nuclear explosion, for example. Okay, so it's really a hard threshold, a 0 or 1. So one way around this is to use what we call soft thresholds. Okay, by softening the threshold function. Okay, so we can use what's called the logistic function, which is defined as 1 over 1 plus e to the negative z for a given value z. So this function has many convenient mathematical properties. Okay, you can see these graphs. So this is on the left here is a hard threshold. So if the output is negative, it's going to give you 0. If the output is positive, it's going to give you 1. What we want is this output right here, which is from the logistic function. You can see that it's much smoother between 0 and 1, and does give you a probability level. Okay. So what we're going to do then is we're going to define our new loss function, which is a logistic regression hypothesis. Instead of just a linear equation and a hard threshold, we're going to say we're going to apply a logistic function to the product of w dot x. So we do the dot product, and instead of using the result to determine the class 0 or 1, so remember in the previous approach we just said if this product gives us a negative number, it's a 0. If it gives us a positive number, it's a 1. What we're going to do is we're going to apply this logistic operation to the result of the multiplication, and then if the result of the logistic operation is bigger than 0.5, so you say there's a more than 50% probability it belongs to class 1, we'll assign it to 1. If it's less than 0.5, we'll assign it to class 0. And that gives you a confidence level as well, because now, even though 2 points, 0.6 and 0.9 will be both classified as 1, but you can move your threshold. You can say, actually, for example, if I'm more interested in capturing a specific class, I'm going to move my threshold. I'm going to require a higher output from the logistic function in order to classify a given data point as a 1, for example. So this concludes this presentation about linear regression and how it's used in continuous prediction and classification. See you in class.